Hello, everyone, and welcome to the grand finale of the PromoMoon 2024 competition. My name is Oleg Vinskovsky. I am with Yuzhny Design Office of Ukraine, and at the same time, I am a member of the board of directors of the Moon Village Association, in charge of the market promotion and coordination. It's my great pleasure and honor to be a moderator of the event today, which is a culmination of the competition in the framework of the PromoMoon, as a joint initiative of the Moon Village Association, or simply MVA, and Yuzhny Design Office of Ukraine. This competition was designed to honor the memory of the general designer, general director of the Yuzhny Design Office for many years, Dr. Alexander Degtyarev. Dr. Degtyarev was not only an excellent engineer and a very successful manager, but also a visionary and innovator with a special passion for the moon, its peaceful exploration and utilization. Importantly, our event today is also a final event in the long series of the festivities in the framework of another very important initiative of the Moon Village Association, which is an International Moon Day, supported by the United Nations. You will hear shortly more about IMD, but now it's a time to introduce our participants. And I start with Giuseppe Ribaldi, President of the Moon Village Association, Senior Advisor on Space Policy, Director of Human Spaceflight at the International Academy of Astronautics. Maxim Degtyarev, General Designer, First Deputy General Director of the Yuzhny State Design Office, Candidate of Technical Sciences, Member of the Advisory Council of the Moon Village Association, IAA member. Nasr Al-Sahaf, International Moon Day Chair. Now, let me introduce our experts. Since it was and it is a joint initiative, we have experts on both sides of the MVA and Yuzhny Design Office, and I start with the MVA experts. They are Christophe Bosquillon, Founder and Chief Executive Officer, Autonomous Space Futures Limited. Christophe is with us today. Hello, Chris. We have four other experts on the MVA side who were not able to join us today, unfortunately, but let me introduce them. Akira Tsuchida, Vice President, RealWorks Japan, LLC. Christophe Bonal, Senior Expert, Maya Space. Bernd Hofer, Chairman and CEO, A9C Capital, WLL. And Francois Dubrul, Founder and CEO, Cosmosis. Now, let me introduce the experts on the Yuzhny side. Evgenia Yermolenko, Head of the Marketing and Strategic Planning Department. Irina Gusarova, Leading Specialist, Spatial Rocket and Space Systems Design Department. Alexander Berdnik, Head of Group, Space Rocket Systems and Launch Vehicles Design Department. Sergei Podolsky, Deputy Chief Designer and Head of Design Bureau, Liquid Rocket Engines. And Andrei Pustovgarov, Head of Group, Ground Infrastructure for Rocket and Rocket Space Systems. And now it's a special pleasure to introduce our winners of this year's competition. And I start with Madison Fian, Space Copy, Regolith Extraction and Processing Technology for Lunar-Enabled Manufacturing from Canada. Hello and congratulations, Madison.
Thank you.
Tetiana Golub, Iron and Steel Institute, named after Nekrasov of the National Academy of Sciences of Ukraine, together with Molchanov Lavr and Borisenko Andriy. Their project is called Development of the Concept of In Situ Thermal Dissociation of Regolith Oxide Compounds under the influence of an electromagnetic field to produce oxygen gas in relation to lunar conditions. The team is from Ukraine. Congratulations, guys.
Thank you. Hello to everyone.
And the third winner is a team led by Alexei Derkach, together with Makarenko Dmitry, Evgeny Muranov, and Oleg Kabat from Dnipro State Agrarian and Economic University. And their project is entitled Development of Materials for Machines that will extract water on the moon. The team is also from Ukraine. Congratulations, Alexei.
Thank you very much.
Team. Hello.
Hello.
With this, let me pass the floor, dear ladies and gentlemen, to Giuseppe Ribaldi, MBA President, for his address to the participants. Giuseppe, the floor is yours, please.
Okay, so first of all, good morning, good afternoon, good evening to everyone around the world, as hopefully they are following us on the YouTube channel via also the MBA website. So first, let me thank you, of course, Dr. Dektario, as well as all the team of Yuzhnoye that in a difficult situation has been able, as always, to produce an excellent work which has brought us today. That is basically the conclusion of the PromoMoon initiative for 2024. So I believe that what today is even more special, if I may say, Oleg, of the other day, because today we have been able to combine this PromoMoon initiative with the last International Moon Day 2024 global event. And that is the reason you will hear later on from Dr. Nasser Al-Saab, the chair, a little bit more detail of the International Moon Day 2024 results. So it is for me a special honor to close, let me say, this year loop of event with this special event with the promotion. And this is also even more, let's say, important because we have two speakers, I suppose, that will speak after me, which are from Lockheed Martin, our main sponsor, and as well as Professor Giancarlo Genta, former from Politecnico of Torino. So PromoMoon initiative, it's something which we have initiated 3 years ago together with Yuzhnoye, and this is coming from a proposal from them, and it is aiming to try to help basically startup by giving coaching of experts so that they can elaborate their, let's say, different type of activity business case. And so we hope that for each of the winner, as been presented earlier by Oleg, will really help them to move forward to the next stage of commercialization. To conclude, given the long sequence of speeches, just to remind you that the Moon Village Association is an NGO created in 2017. The main feature is to be neutral and to be informal. And with that feature, we have been able to bring together more than 60 to 65 country representatives, and we are participating very actively to all the event of the UN COPOS, since we are permanent observer. And so I think it's important that the moon is a laboratory of peace, and we try to bring our small contribution to this end. So with that, thank you again to everyone, and Oleg in particular as well. And I give the floor back to you, and I wish you an excellent event. Thank you.
Thank you so much for your message, Giuseppe Ribaldi. And now I give the floor to Maxim Degtyarev, General Designer, First Deputy General Director of the Yuzhnoye Design Office. Maxim, the floor is yours, please.
Добрий вечір, пані та панове, пане Вінсковський, пане Рибальді, команди та глядачі нашого заходу. Вітаю ж також представників Moon Village Association, які приєдналися до третьої ініціативи PromoMoon, присвяченої пам'яті доктора Олександра Дегтярьова, а саме пана Баскійоне та пана Альсахафа.
Good morning, ladies and gentlemen, Mr. Ribaldi, Mr. Linskovsky, teams and viewers of our event. I would also like to welcome Mr. Bosquillon and Mr. Al-Sahaf, the Moon Village Association representatives who joined the third PromoMoon initiative for Moon Village Generation in honor of Dr. Alexander Degtyaryov.
Сьогодні ми зібралися тут для церемонії закриття вже третьої нашої ініціативи, яка спрямована на пошук та залучення захоплених ідеєю освоєння місяця вчених та інженерів по всьому світу.
Today we have gathered here for the closing session of our third initiative, which is aimed at finding and attracting scientists and engineers around the world who are passionate about the idea of exploring the moon.
Наша основна місія – це натхнення сучасного покоління на розвиток ідей постійного та ефективного освоєння місяця.
Our main mission is to inspire the modern generation to develop the ideas of permanent and efficient exploration of the moon.
Створення нових концепцій і втілення їх у реальність стає складним і важким, коли справа стосується освоєння космосу та інших небесних тіл. І в умовах космічного вакууму, невагомості та низьких температур практично всі процеси протікають не так, як на Землі. Тому, безумовно, об'єднання фахівців з усього світу для вирішення цих завдань є єдиним правильним підходом.
Generating new concepts and turning them into reality becomes a complex and difficult task when it comes to the exploration of space and celestial bodies. In the condition of space vacuum, zero gravity, and low temperatures, almost all processes run differently than on Earth. So, of course, bringing together experts from around the world to meet the challenges arising in such environment is the only correct approach.
Тому ми прагнемо підтримати всі концепції ентузіастів, стартапів та ініціативних груп з усього світу. Хочу подякувати Moon Village Association за організацію цього міжнародного конкурсу, а також усім нашим учасникам, нашим експертам та глядачам, які дивляться цю церемонію закриття.
That is why we aim to support and validate all the concepts proposed by enthusiasts, startups, and initiative groups from all over the world. I would like to thank the Moon Village Association for organizing this international competition, as well as all the participants, our experts, and viewers watching this closing ceremony.
У рамках конкурсу наші експерти ретельно відібрали 3 найкращі проекти з понад усіх. Цими проектами виявилися такі: Regolith Extraction and Processing Technology for Lunar Enabled Manufacturing, стартап від Space Канада. Проект Development of the Concept of In-Situ Thermal Dissociation of Regolith Oxide Compounds under the influence of an electromagnetic field to produce oxygen gas and in relation to lunar conditions. Інститут чорної металургії Україна. Та третій проект Development of Materials for Machines that will extract water on the moon. Також українські учасники Дніпропетровський аграрно-економічний університет.
As part of this competition, our experts carefully selected 3 best projects among all that we received. The best projects are Regolith Extraction and Processing Technology for Lunar-Enabled Manufacturing by startup Space Copy from Canada, development of the concept of in-situ thermal dissociation of regolith oxide compounds under the influence of an electromagnetic field to produce oxygen gas in relation to lunar conditions by Iron and Steel Institute from Ukraine, and the third project, development of materials for machines that will extract water on the moon by Dnipro State Agrarian and Economic University from Ukraine.
Дуже добре, що керівники цих проєктів пані Медісон Фіан, пан Лавр Молчанов та пан Олексій Деркач та їхні команди сьогодні з нами. Вони продемонстрували інноваційні ідеї, які роблять важливий внесок у розвиток технології освоєння місяця. Всі проєкти-переможці цього року спрямовані, перш за все, на використання місцевих ресурсів на місяці і тому мають безперечну практичну значимість.
We are happy to have with us today the managers of these projects, Madison Fian, Laura Molchanov, Alexei Derkach, and their teams. They demonstrated innovative ideas that make an important contribution to the development of lunar exploration technologies. All the winning projects this year are aimed at using local resources on the moon and have undeniable practical significance.
Ми раді тому, що серед нас є такі талановиті та креативні люди, і пишаємося тим, що цього року серед них вперше опинилися українські вчені. Дякую.
We are happy to have among us such talented and creative people, and we are so proud that Ukrainian scientists took part in the competition for the first time this year. Thank you.
Shcheryov. Now I pass the floor to Dr. Nasr Al-Sakhaf. Nasr, please present us the International Moon Day. Thank you.
Thank you. First of all, thank you all for this wonderful opportunity to share with you information about the International Moon Day. As you know, the International Moon Day was declared in December 9th, 2021 by the United Nations General Assembly. It was in response to an initiative by the Moon Village Association, because there was a lot of countries trying to reach the moon by 2030. And as from my experience, heading the Saudi delegation to the COPUS in 2008 and 2009, I understand the bureaucracy of the United Nations. However, the importance of the International Moon Day played a great role by having it approved within the same year that it was actually proposed by the MVA. And so this in itself is a signal to the world of how important moon exploration is to mankind. So we started, the first year was in 2022, celebrating the International Moon Day on the 20th of July as the main event. However, there are also global events that start within that week. So it runs for a whole week, actually, and not just one day. So the first one was celebrated in Huntsville, Alabama, in the United States, home of the Saturn V rockets, which propelled the Apollo program to the moon more than 50 years ago. Now, we're going back to the moon. Humanity, we're going back to the moon because now there is evidence that there is water in the south pole of the moon. So this gives a big opportunity for lunar exploration for all mankind and cooperation. This will give us a chance to explore the whole universe and outside of our solar system and into Mars and into other planets. So the second day was in last year in 2023, which was in Seoul, Korea, and that was also very successful. And the participations grew from the first year of about 23 countries and 38 main event plus global events. It grew last year to almost 50 countries, 48 countries to be exact, and 50 global events, including the main IMD event in Seoul, Korea. This year, we had two main events, one in Harbin, China, and another one in Vostok, Germany. And so the total numbers were about 41 countries, and I believe 42 main events and global events all together. And so this is going and growing successfully throughout the years, and we are looking forward to growing even more in 2025. We will definitely announce our venue for the IMD 2025 this December 15th in 2024. So I hope that we will have all of you participating in a global event, and hopefully one day we will have the main event also in Ukraine. With that, I give back the floor. Thank you so much.
Dr. Al-Sahaf, for your message. And now I would like to introduce our keynote speakers for today. Giuseppe Ribaldi has already mentioned that we have two keynote speakers, and they are Luis Cario from the Lockheed Martin Corporation, our main sponsor. Hello, Luis.
Hello, Oleg.
And Professor Giancarlo Genta, Professor Emeritus at Politecnico di Torino, member of the International Astronautical Academy. Hello, Giancarlo.
Hello to everybody.
Thank you to be with us, Luis and Giancarlo. And I start with Luis Cario. Luis, the floor is yours for your short keynote speech. Thank you.
All right. Good morning. Thank you very much for the warm introduction. I'm here today to share some thoughts on water-based nuclear-enabled lunar infrastructure, focusing first on the nuclear aspect, including some of Lockheed Martin's technical developments in this area, some system of systems analysis work that we've done within this area, and discuss how nuclear can enable ISRU water surface production systems to support future cislunar economy. So, as likely everyone here is aware, it's been over 50 years since humans have been on the moon. And as we return to the moon, there's international alignment that return should be sustainable. And by sustainable, well, we mean that we're able to sustain an indefinite presence there. A sustainable lunar architecture will require lunar infrastructure. And by infrastructure, I'm referring to the systems upon which other systems rely in order to execute a given mission. Power as infrastructure will be a fundamental backbone for lunar infrastructure. And its deployment is called out explicitly in the NASA's Moon to Mars objectives. As part of those objectives, they also refer to the deployment of ISRU-based capabilities enabled by that power infrastructure. Consistent with this, fission surface power, or FSP, as I may allude to in this presentation, is best suited to enable this industrial scale surface architecture, for reasons I'll discuss in a short bit, but which is echoed in NASA's Moon to Mars architecture document. From reading these documents, our perspectives culminate to a vision of a collaborative lunar surface power architecture. There's a lot of context to talk about in this chart, but the main takeaway I wish to relay is that we are small and at the beginning, but we are designing in a way that has the endpoint in mind. And we see surface systems as evolving both over time, the distance, and scale, consistent with the Artemis campaign, starting with fixed site infrastructure and evolving support infrastructure across the various systems that we will deploy, including ISRU production in the crater rim context, consistent with eventually achieving cislunar economy. Now, we may not ultimately realize a full industrial scale context. However, at a minimum, it's important to begin that exercise designing with that potential at scale. It's also worth noting that while we this shows one fully interconnected grid context, there's no reason, especially during initial growth, that we would not expect early development to be independent microgrids, although in the indefinite future, we would expect that it would be preferred to interconnect these to increase system resilience over time. In the bottom left here, you can see FSP, but what doesn't come across is the magnitude of the load that this supports, as well as the production levels in the crater rim. So I'll talk about that for a moment. To give a sense of the initial technology development that we're using as a basis for some of these concepts, we're leveraging our design work on fission surface power, specifically an FSP element that was designed capable of generating 40 kilowatts of electrical energy continuous on the lunar surface and through the lunar night. This design was executed in partnership with Criari for their high-efficiency Brayton power conversion, and in partnership with BWXT for the monolithic core fusion reactor using HALEU, the high-assay low-enrichment uranium designs. And additionally, the design also includes Lockheed Martin's ultralight titanium deployable radiators for thermal rejection. The design is highly scalable and much easier to scale upwards and flexible to accommodate a wide range of lunar users on the moon. So one of the major analyses that we've completed recently includes generating optimized lunar power grid designs for a number of potential lunar surface sites with various lighting conditions, including comparisons between fully LVSAT, so lunar vertical solar array photovoltaics technology based power generation, and those that are supplemented by fission surface power. And this analysis involved auto-generating a number of elements, power generation elements, power management and distribution, grid nodes, surface harnessing, energy storage elements, and etc., and their placement to resolve a lunar surface grid design. To normalize our results for this particular analysis, a constant power demand is assumed at a variety of locations, and it's not shown in this chart, I apologize, but across these different sites that they vary the normalized illumination seen over the course of a lunar day, with sites 1 through 4, or sites sites 1 through 4 having a high degree of sunlight throughout the lunar day, whereas sites 8 through 10 having much worse lighting conditions. The consistent with these results, it also accounts for the differences in slope impacts with element placement, harness routing, and each of these grid areas are costed with respect to recurring engineering costs, operational costs that are shown in the top 2 charts, as well as launch vehicle costs using course parametrics shown in the bottom 2 charts. And so the results of this analysis effectively highlight the favorability of illumination with respect to a decrement in the power system's cost, as sites 1 through 4 have near constant illumination, and they don't require the additional energy storage elements aside from the LVSAT's energy storage, nor particularly long harness distance to meet those power generation needs. It also shows really the relative impact that energy storage elements have on driving the total grid system costs, largely in the form of launch vehicle costs. This is something that's easy to understand intuitively, but seeing the numerical relationships really drive the point home. And also highlights the relative normalized illumination threshold, or more aptly, the lunar night energy storage demand, where it ultimately becomes more cost-effective to rely upon fission power as opposed to lithium-ion batteries and surface photovoltaics. We've done this analysis using different types of energy storage technologies, including regenerative fuel cells, and we find that the threshold of cost optimization is around the 2 megawatt hours or so during the lunar night. So this type of analysis approach can easily be applied to compare and contrast, different identified lunar sites favorable for water-based ISRU production, and update as we learn more ground truth about the lunar South Pole. And by performing these analyses in this type of approach, it helps communicate where we think the highest value opportunities are located and how we should be focusing our efforts. Something else we focused on earlier in this year, and I'll show a little bit more on the following slide, is that generating lunar surface architectures in an object-oriented model-based system engineering framework to do systems of system analysis across disparate infrastructure systems. A lot of that work focuses on water-based ISRU system architectures, understanding various topologies and how their throughput scales with power consumption. The data artifact on the right here are exports from our scalable ISRU Simulink model that we've built, focused on the production of water and cryogenic propellants. So liquid hydrogen, liquid oxygen, to better understand system behavior and trade technology developments. The original question we really wanted to understand is how many flavors of each type of surface element are really needed to meet a given propellant demand, and how does that scale with increasing demand over time? Noting that a water-based ISRU system will span from being inside a crater to the crater rim, it's important to know how much power is needed, but it's equally, if not more important, to understand exactly where that power is needed. The pie chart on the top right here shows a percentage of the overall power used by each type of element in the ISRU process, and whether that element is either at the crater rim or deep inside the crater. This is important because it's more difficult to provide power inside the lunar crater versus the crater rim. In this model, we can see there's far more power needed outside of the crater rim than inside, and arguably by design. And we can also use this data to draw conclusions about our technical needs and make recommendations regarding technology development focus areas, like the fact that electrolysis and liquefaction are by far the greatest drivers for the power demand on the surface systems, and thus highlight disproportionate value proposition for improving their respective performances. So while those are static concepts, the time phase buildup is also really critical to understand, as we expect demand for water and cryogenic propellants to increase over time, which helps establish the basis for understanding the relationship between demand forecasting and operational scalability of both systems. Within that ISRU cryogenic propellant production architecture explicitly, we've run a suite of analyses associated with different types of functions and their pairings for allocated within specific elements. For example, should a surface excavator include separation? Should that be done with separate infrastructure, mobile or fixed, etc.? And we compared figures of merit based on power distribution, production throughput rate, down mass throughput per kilowatt hour, etc. And the results of this initial study indicate that having optical power distribution to mobile elements within a permanently shadowed region enables a higher production mass throughput comparatively. And this also tracks intuitively as a concept of operations that requires regular return to a centralized charging hub, otherwise sees more system downtime that reduces the projected throughput. In general, optical power beaming as a means of power distribution is also more amenable to efficient surface power generation, since the change in cost for a corresponding increase in power production should be less than that of photovoltaics and energy storage due to the cost of that energy storage and how that scales with power. It also means we're better able to make up relatively higher distribution losses that are associated with optical power distribution. So consistent with this architecture, or that architecture, depending on the set of assumptions going in, you can have widely different expectations of power needs for those associated systems. In general, power demands from ISRU systems dominate total power demand projections, and that power use effectively scales linearly with commodity production demands. The numbers that you see in these charts represent a speculative ISRU system infrastructure for cryogenic propellant production, increased over time, but sufficient to replenish a representative reusable liquid oxygen, liquid hydrogen lander in NRHO at a rate of about 1 mission per year. And so in comparing values between Lockheed Martin generated analyses and using metrics that published by NASA, there is the variation that's shown here is up to 4 times overall power system demand per mass throughput. And extrapolating from that, if you account for demand for Mars transit, the sustainable exploration, etc., we think that the commercial demand for the cislunar ecosystem can be up to 50 times these values using provided use of a single stage lander architecture. And so when I say that is not to assert that either one of these is correct here, but that scale really matters, and this is really important in that those different underlying assumptions can significantly drive the system infrastructure and their relative sizing. And so it is something that we need to work harder on and make sure that we get right. Having built those tools, we're now presently in the process of laying out full-up lunar surface architectures that include virtual representations consistent with the data models that are on the back end that we've been analyzing too. On the left here, you can see a lunar surface architecture that we generated using some of our early back-end modeling. These data artifacts were then modeled in Unreal Engine to provide a better context for understanding how these architectures work and how lunar surface systems would interact with them. This is not an actual lunar location per se. It was captured to show localized co-location of core lunar infrastructure and understand how to lay out these systems. This is a short visual of our Unreal model in action, captured from the perspective of a crew member within a lunar mobility vehicle. And some of the material that we'll be generating and publishing in the short near future will show some of our work for specific layouts on the lunar surface. So in summary, I hope you've walked away with a bit of some context perspectives on how nuclear power will functionally enable our water and cryogenic propellant production for a sustainable presence on the moon and our continued space exploration. We do feel that nuclear power is ideal to address the lunar power generation needs at scale and to more cost effectively achieve a year-round population on the lunar South Pole. That the commercial scale generation needs for ISRU really do require that nuclear power systems to be cost effective, and that understanding how power and ISRU production systems are required to scale with that sustainable presence is really important for our future surface architectures. And lastly, Lockheed Martin Space has recently penned a novella that captures a vision of humanity's future in space, in addition to a longer vehicle tour of our Unreal Engine models. And so I invite you to explore those at your leisure. I will not be at IAC, but many of my colleagues will be at IAC. And I encourage you to reach out to them at the Global Networking Forum panel and the technical paper that we'll be presenting on lunar surface architecture modeling. So thank you.
Thank you so much, Luis, for this very interesting overview of the Lockheed Martin recent developments in the field and for your announcements. And now I would like to pass the floor to Professor Emeritus at Politecnico di Torino, Professor Giancarlo Genta, for his keynote presentation called Enabling Technologies for the Moon Colonization. Giancarlo.
All right. Good morning to everybody. First thing, I shall open my screen. Okay, do you see my screen? Perfect, so I can start. Okay, so you don't see? Oh, just a moment. Now? Perfect. So often we say that we have the technology for the moon. This is partially true because 50 years ago, the Apollo program went on without problems, and 12 human beings landed on the moon surface. They came back without problems. There was no accident on the moon. 11 Apollo missions with crew left the Earth from Apollo 7 to Apollo 17. not all landed on the moon, but all went in beyond Earth orbit, except one, which was a test in orbit. 10 were successful. Only one had a mission failure, but even the one which had a mission failure didn't finish with loss of lives, and all astronauts came back successfully. Okay, the program was terminated earlier, but the missions that were made reached successfully the technological, scientific, and political goals of the program. So the Apollo program was a big success, and from that we can state that in the 60s we developed technologies which allowed us to reach the moon and to come back safely. We must add that these technologies not only allowed us to reach the moon and to come back, but also to change deeply technology on Earth. So they had a fallout of technological innovation. It's enough to say that modern methods using computers to design anything from cars to power plants to anything are derived from the innovation that in the 60s allowed us to go to the moon. So going to the moon was not only successful in itself in the sense that it reached its goal, but also was successful in the sense that they allowed us to make many technological innovation to use on the Earth. But this was for missions that were more or less what we call flag and footprint missions. No human being remained on the moon for long times. The explored zones were small zones about the landing spot, and above all, no human being had to survive the long lunar night. So we can safely say that while the Apollo mission technologies were successful to carry us to the moon, they are not successful for remaining on the moon, colonizing the moon, settling the moon, which is exactly what we want to make now, because we are returning to the moon, not for flag and footprint missions, but to explore the moon in larger scale, survey for resources, water and minerals, and building materials, even perhaps helium-3, even if this is controversial, because we don't know whether we really need helium-3, because we don't have any, for now, power station running on helium-3 on Earth, and we don't know how to build one on the moon. We must start a lunar economy and to start a lunar industry, using the moon as a training ground for learning how to live in extraterrestrial environment in such a way that we can become a multiplanetary species. So to do all these things, we need to develop new technologies. And what are these new technologies? Well, they are many, but I identified 9 of them, 7 of them, sorry, that I listed here. We should improve our rockets to lift off from Earth. We should improve the deep space propulsion we have. We should learn how to build habitats on the moon. We should learn how to protect ourselves from radiations when we are on the moon. We should develop regenerative life support systems. We need the power generation systems. And I agree with the speaker who spoke before me that these power systems must be nuclear, and we must develop additive manufacturing, particularly suited for moon operations. So these are technologies we must develop, but here I added a lot of empty lines just to say that they are not enough, and there are many other technologies that are needed, and some of them we cannot predict which they are. Only experience on the moon will tell us what other technologies we must develop. By the way, this is something which always happened in history. Every time humans enlarged its sphere of living, they had to develop new technologies to allow them to live there. The oldest things were clothing and habitation. When humans left East Africa, where they developed, and went to colder places. And speaking of the moon, I always speak about the technologies that humans had to develop to live in Arctic regions. In ancient time, for example, the Inuit had to develop glasses, not glasses because they were not glasses, but they were wooden devices with a small slit to prevent of losing their sight due to the reflection from the ice, the sun on the ice. I always say that for them to develop this protection of the eyes from the reflection of the sun was like for us to develop proper spacesuit helmets, and for their technology it was an innovation as big as for our technology will be an innovation, spacesuits adapted for the moon. Okay, the first technology I spoke about was rockets to lift off from Earth. Apollo program relied on chemical propulsion, with the Saturn V, which was a much successful launcher, but was very costly. If we wanted to go reliably to the moon and continuously, we must develop much cheaper launch systems. And here I mention the Super Heavy Starship complex that has a version developed for the moon, the HLS Starship, that will cut costs very much. And we must say that only the increasing role of private companies can allow us to go much more cheaply and more affordably to the moon. So this is a first point. I am sure that only when the Starship Super Heavy complex will be tested successfully, and we all hope that this will happen within this year, we will be sure that we have really a cheap access not only to the moon, but also to Mars, because originally the Starship rocket was developed for Mars and then now is being adapted to the moon. Particularly the way of landing vertically backwards will be really something that will facilitate landing on the moon. All right. Then we must speak about deep space propulsion. This is not really necessary because with the Starship we will go to the moon with chemical propulsion, but and will allow us to reach the moon in just 4 days, like in Apollo program. But to reach Mars, we need to develop more advanced deep space propulsion systems. And once we have developed them, they will prove to be also very successful for the moon. Nuclear thermal propulsion will be the first to be developed, and the Draco demonstrator, here we have the artist impression of the Draco system, is thought to operate close to the moon. So it is a lunar nuclear spaceship, and in the acronym Draco, C stand for cislunar. When we have nuclear thermal rockets based on fission, we could reach the moon in 2 days instead of 4, and in a cheaper way. But for Mars, we need to go beyond nuclear thermal rocket based on fission, and there are many research groups, particularly the one working at Princeton University, that are developed nuclear fusion drives. DFD, for example, is a good candidate not only for Mars, but also for the moon. And simple computation allow us to say that with DFD, we could reach the moon in less than 1 day. That is cutting travel times and also cutting costs. On the contrary, nuclear electric propulsion, which will be very useful for Mars, is not really suited for lunar missions. Even if we have a very advanced nuclear electric propulsion, allowing us to reach Mars in 3 months or something like that, we will need 10 days to reach the moon. So nuclear electric propulsion is not the best candidate for human missions to the moon. On the contrary, it will allow us to build cargo ships to carry a lot of objects to the moon with very low cost, because it is efficient in terms of propellant, but is not efficient in terms of travel time. Oh, by the way, I will add that even if our wildest dreams about propulsion would come true, which I don't believe, that is, even if we will develop a space drive, well, this will not be really suitable for the moon, while they are for Mars, but is like nuclear electric propulsion, that is low thrust systems which are suitable to work in interplanetary environment, but not in the high gravitational field we have from Earth, and which dominates in the whole Earth-Moon travel. All right. Another technology we have developed is habitat construction, and for the moon, to settle the moon, We cannot live in metal habitats, what we call tin can habitats, like the one we have designed for space stations, because, or even inflatable habitats. The best thing is to build habitats using lunar regolith, which allows us to protect us also from radiation, not only from the space vacuum. We can do that in many ways, making regolith bricks, for example, to build an habitat. This is difficult to make in automatic way, and also it gives us a problem. Bricks are unsuitable for tensile stresses, and in a lunar habitat and also in a Mars habitat, the stresses in the building, unlike what happens on Earth, are tensile and not compressive. So brick structures are unsuitable. So we need to make something different. 3D printers can build concrete made from lunar material, concrete-like materials, which can be standard type, that is made like concrete on Earth, which is difficult in vacuum, and also it is not very suitable for tensile stresses, or fusing the regolith, what usually is called fused lava material, or laser sintered materials. There are a lot of research groups working on that, both in ESA and NASA, and also other space agencies are working on that. And this, I think, is the way we will go. Protection from radiation is very important for permanently inhabit the moon. The thick walls, regolith buildings is enough, but we cannot have windows in these buildings. The same for underground buildings, will not have windows, but we need windows for mostly psychological and safety reasons, and we can use virtual windows, that is outside the camera, a TV camera, and inside a big screen which simulates the windows. But normal screens, which now are very cheap and very light, like thin film screens, are not the best because they supply a two-dimensional image, while we need three-dimensional images not to lose our ability to see distances. So we must develop autostereoscopic technology, that is screens that give us a three-dimensional image, even if we don't carry glasses for like the three-dimensional screens we use now. Well, autostereoscopic technology is in development because it's very important in the cinema industry, and we can hope that in a reasonable time we will have autostereoscopic screens that allow us to build true virtual windows, and this is important in the field of passive radiation protection. But there is also the possibility of developing active radiation protection using building a sort of magnetosphere for the habitat, but this is still a technology we need to develop. Studies are going on, but we still need time. active radiation protection is also very useful to protect spacecraft. So for the travel, this is more important for Mars than for the Moon, because the Moon, the travel is short, as we have said, but is important also for that. Regenerative life support systems are important. They are more important for Mars than for the Moon, but also for the Moon. But they have not a sufficient technology readiness level. So this is other technologies to be developed. Regenerative life support systems are essential for becoming a spacefaring civilization. It can be developed in steps. Partially regenerative systems, life support systems, are not so difficult to develop, and they are very good for the Moon. So if we can bring consumables from Earth, partially regenerative systems are enough. The Moon is close enough for this, but Mars is not close enough. So for Mars, we need fully regenerative systems to stay on Mars for a long time. But for the Moon, partially regenerative systems is enough. We must develop hydroponic or better aeroponic greenhouses. Now I am working on that, so I got some experience on that, and also artificial meat production plants for microgravity and lunar and Martian gravity, because it's better to produce the food on the Moon so that the outpost and then the habitats, big habitats on the Moon, can be more self-sufficient. Well, time is passing, so I must go fast. For power generation, we need nuclear power on the Moon. The previous speaker has said very well these concepts. In the polar regions, we need nuclear power, but above all, in non-polar regions, we need nuclear power, because we have long nights. In polar regions, there are regions that are fairly lighted for long times, but in non-polar regions, we take the whole lunar night when we need the maximum power and we don't have solar power. By the way, very recent studies have shown that on the Moon there is much water even in non-polar regions, which means that perhaps we will not be required to live in polar zones, which are much more difficult to reach and much more difficult to live on. So if we have water also in other places, these other places can be open to settling, but here we need really nuclear power, fission nuclear power. Additive manufacturing is very important for building the habitat, but also metal and plastics additive manufacturing to build machinery, first spare parts and then machinery. It's very important that we learn how to produce on the Moon materials for additive manufacturing. By the way, I heard that one of the winner of this competition is about producing oxygen on the moon from regolith. This is very important because oxygen from regolith is obtained from oxides. And when you obtain oxygen as a byproduct, you can have aluminum, you can have titanium, you can have iron, and so on. So if you can make from this easily powder with additive manufacturing, you can build machinery. The moon will become the shipyard because if you build a spacecraft for going to Mars and the whole solar system on the moon, you will not have to live with big spaceships, the gravitational well of Earth. So the construction of spacecraft on the moon is very important. Additive manufacturing is being developed on Earth, but additive manufacturing is much sensitive to gravity, so additive manufacturing machines to work on the moon and in space must be developed. Some of them are in development. There is an additive manufacturing machine on the International Space Station. So this is a research that is going on, but is a technology to be perfected. So as a conclusion, we can say one important thing, that we to settle on the moon and to become a multiplanetary species, we must develop new technologies. Apollo program, in a way, was like Vikings of the 11th century who reached the American shores and started colonization of North America, but failed because when the temperature decreased after the hot period of the Middle Ages to the small ice age of the 15th, 14th century, America was abandoned. Why? Because Vikings didn't have the technology to really go to the America and stay there. European 500 years later had developed the navigation technology that allowed them to settle North America. So the same thing we must do for the moon. We went to the moon with a technology with sufficient to go there, but not to settle there. And now, if we don't want to do like the Vikings that failed in colonizing North America, we must develop new technology. And private industry has a large role to play in starting lunar economy and in reducing cost to go into space in general and reducing cost to go to the moon. And with this, I can finish my presentation. Oh, by the way, I apologize, but I have to leave you early because 2 days ago I had a small eye surgery and I cannot remain in front of a screen, a computer screen, for a long time.
Okay, Professor Genta, thank you so much for your very insightful presentation on the enabling technologies for the moon colonization. Let me wholeheartedly thank all our keynote speakers, that is 2 of them. And of course, Professor Genta, it's quite understandable that you should leave right now. Thank you so much once again, both Luis and Giancarlo. And let me move to the next agenda item on our plan today.
is no more condivided. It's
Yes,
okay?
it's okay. It's okay.
Okay,
Yes.
perfect.
Thank you.
So, thank you.
So we are moving to the presentation of the winning projects. And we start with our Canadian winner, and I give the floor for the presentation of the project called Space Copy, Regulated Extraction and Processing Technology for Lunar-Enabled Manufacturing, to Madison Theon. Madison, the floor is yours, please.
Thank you, Oleg. Dobry ranok. Dziękuję za uwagę. Good morning, and thank you all very much for your attention today. I will begin by sharing a presentation to describe the technologies pioneered by Space Copy. It is my great honor as a Ukrainian Canadian to be able to share the technology that we are building here. And with this, I would like to first begin my presentation by explaining to everyone a little bit about what we are doing at Space Copy. Space Copy is an additive manufacturing and materials engineering company based in Canada and the United States, and we are proudly developing novel 3D printing technology for infrastructure development in extreme environments, space and on Earth, for applications in construction, infrastructure development, military, and defense. Some of the tasks that we perform in terrestrial locations here on Earth include infrastructure development in extreme terrestrial climates, such as the Arctic, desert, subsea, combat zones, natural disaster areas, as well as in space for microgravity, and the long-term goal of lunar construction. First, I would like to explain the vision behind why we started Space Copy. Space Copy was founded in 2022 to solve a very unique challenge. As was discussed by some of our keynote speakers, the cost and weight of transporting supplies from Earth to the Moon are astronomical. Current payload costs are equating to $1.2 million per kilogram in order to send a payload into the most remote areas on Earth, as well as in space. And coupling this with the Artemis return back to the lunar surface and the South Pole as early as 2028, it can be approximated that over 22,000 kilograms of supplies will be required to sustain a crew of 4 astronauts just for 1 year. We realize that this problem is absolutely unachievable. And at Space Copy, we saw this vision and pioneered an additive manufacturing technology that was able to remediate this challenge and also have a dual-use purpose here on Earth for developing infrastructure in extreme environments and natural disaster areas. The solution that Space Copy has built out with its 4-stage printing technology can be explained as follows. The first stage is what we refer to as mixing, or a more technical term, beneficiation. We create a custom feedstock using lunar regolith through an in-situ resource utilization process that involves crushing, sieving, and breaking down the powder into a usable feedstock, and then we process it to obtain the most high-quality minerals that will benefit the strength and density and duration of that infrastructure. The second stage is what we refer to as feedstock sampling. With the use of high-technology Raman spectroscopy lasers, we are able to scan and analyze this feedstock to determine a mineralogy composition that is used to enhance the 3D printer's process parameters. This can increase things like nozzle temperature, laser heat, as well as printing deposition and hatch spacing to ensure denser and more robust parts being delivered on a shorter time with less material being consumed. Our 3D printing system is, of course, the third stage. We utilize 2 different systems for building a various array of infrastructure, ranging from a precision tooling fabrication and small geometries to repair equipment, which is used via selective laser melting, and for larger scale infrastructure to support habitat development, roadways, launch pads, berms, trusses, and much, much more. We utilize a fused deposition modeling technology, also known as FDM printing. To wrap this up, stage 4 is what we refer to as AI and autonomy. Every step that I have just described to you all is 100% powered with artificial intelligence algorithms, allowing this smart manufacturing system to be able to operate remotely, regardless of the presence of astronauts. Here you can see a schematic interpretation of the technology that we are developing. This is the FDM printing system suitable for larger scale infrastructure development, with the beneficiation system that breaks down the lunar regolith into a feedstock visible on the far left-hand side of the mechanism. Now, in order to achieve this incredible feat requires international collaboration from a variety of different partners across the globe. As a cross-continental and international company, we are proudly partnered with various academic, government, and private industry partners from around the world. From left to right, you can see our partners in academia, such as Johns Hopkins University and the University of Alberta. And from the right-hand side, we transition to clients in space agencies, contracts with private space companies, and features, such as our work alongside the Techstars, MIT, as well as Singapore Management University, and our proud features in Business Insider and NBC News. Our current progress as a company is at a TRL3, or Technology Readiness Level 3. As we transition into the TRL4 stage throughout 2025, we are seeking to enter more into a customer discovery phase where we are understanding the benefit of this technology from a commercial perspective. Coupling technical expertise with business industry knowledge, our team is oriented towards finding a solution to this technology that allows us to be able to bring this technology to light for its most useful applications. We are also patent pending and have multiple contracts in place, including letters of intent and memorandums of understanding with some of the world's largest space organizations, including NASA. One of the proud features that I would like to showcase today is how we've gotten to this stage. Our TRL3 milestone achievement was the development of 3D printed bricks created from a lunar regolith simulant, coupled to be 99.9% accurate to Apollo-era lunar soil. So starting from left to right at the top of my screen, you can see the transition of lunar regolith into 3D printed bricks. The top right photo features FDM 3D printing with a small amount of thermoplastic additives, and the bottom pictures comprise the selective laser melting and sintering technologies that were used to prove out as a proof of concept testing in our phase 1 development. We have since moved into precision tooling fabrication, and we will be conducting mechanical testing to ensure the strength of our tooling, as well as improving the granular uniformity of simulants to create a more even particle size distribution, which is absolutely critical to being able to achieve additive manufacturing in the harsh environmental conditions in space, which feature extreme thermal gradients ranging from negative 173 to positive 125 degrees centigrade, as well as the space radiation, and of course, the vacuum environment of space, which proves to be a very challenging feat. Aside from this technology development effort, Space Copy has been proudly featured in various different awards across the globe, spanning from the Middle East to Europe, to North America. We have proudly taken home many awards and government contracts with esteemed organizations, including our proud feature in this year's PromoMoon initiative, as well as taking home the Aldrin Family Foundation Global Innovation Award this past spring. We have multiple initiatives already in place, as well as peer reviews and journal features publicly available for those who would like to learn more about the inner facets of our technology development. With regards to our team, we are truly multifaceted. Balancing technical and business knowledge, we are able to communicate and develop out this technology with special attention to the array of different challenges that we have in front of us. Myself, personally, I have a background in business and commerce with Harvard Business School, and also with prior NASA experience working in planetary science, heliophysics, and astrophysics, where I gained a lot of knowledge and a lot of inspiration with regards to how we are able to send humans back to space. And that is a core vision behind Space Copy. I also do volunteering work as a subcommittee advisor to UN COPUS, and I am a proud member of the Moon Village Association and the G100 Chair of Space Technology and Aviation for the province of Alberta, Canada. In addition, our team of advisors who are working alongside us to develop out this technology have a combined over 80 years experience in the fields of entrepreneurship for space technology, and we are extremely confident in our ability to bring this technology to light, not only for the benefit of humanity from a terrestrial aspect, developing infrastructure on Earth, but also to power future generations in space and propel the lunar economy in a tangible manner that supports ongoing logistics and goals set out by the Moon to Mars objectives, as well as some of the goals highlighted as far back as the Outer Space Treaty. I would like to thank you all for your attention to this presentation. If you'd like to learn more about the additive manufacturing technology pioneered by SpaceCopy, I encourage you to visit spacecopy.com. And for anybody attending IAC in Milan, I will be speaking a handful of times to showcase this technology further. Thank you so much.
Madison, thank you very much indeed for your very impressive presentation. And now we are going to hear what the experts say on your presentation. I will start with the experts on the MVA side. I will read their comments, and then I will pass the floor to Dr. Maxim Degtyaryov for the comments from the Yuzhny experts. So, what Akira Tsuchida says. Team SpaceCopy prepared a good summary of their project, including reasonable estimation of TRL at the level 3, competitors, for example, Redwire, Icon, Sysloon. As an expert for Moon surface and Artemis gateway development, I would like to know about potential risks when SpaceCopy start actual development, such as mission design overview, what and how much resources are required for first mission to evaluate your system. What technologies challenges are expected to operate on the Moon surface. Bernd Hofer, a series of customizable multi-purpose 3D printers combining soil sampling, data analysis, AI ML, and 3D printing into one mechanism, improving infrastructure development for extreme environments on Earth and in space is the holy grail for developing Moon economies. Obviously, all the cutting-edge technologies on Earth, such as SLM, AI/ML, spectroscopy, 3D printing, and others, are to be used integrated in a sequence or in parallel. Accordingly, the project endeavor is extremely complex. According to the authors, the TRL is 3, which seems plausible and shows the author's sense for reality. Even if SpaceCopy is a pre-revenue company, it seems to be very important that the company has terrestrial applications projects too to validate the concept. At the same time, it's a great candidate for analog habitats, particularly those which can truly simulate regolith. Obviously, grant applications and cooperations require management attention and management resources. It is highly recommended to look out for an investment partner to fund all or at least most of the development path to build a minimal viable product as soon as possible. Christophe Bonal, this is just excellent. The proposal is good, well constructed and complete. Good additional documentation. The idea is very good. It is not the first time we read about 3D printing on the Moon based on regolith, but this one is very convincing. And numerous potential applications. The experiments so far are significant with nice artifacts produced. Good mechanical behavior demonstrated. However, transposition to lunar condition has to be demonstrated. Vacuum, low gravity, thermal control, dust, etc. A market RL equals 4, technology RL equals 3 appear very justified. Numerous customers identified, contracts pending, and several confirmed LOIs. A global timing is well in phase with current lunar exploration plans, or even too early. Prototype 2025, space launch 2028. Space demonstration before Moon is not clear. Collection of regolith on the surface is not described. Characterization by spectral analysis is not clear. Requirements for additive and binders are not clear. The financial approach is sound. The team is excellent and has an extensive experience with good mentors. Christophe Bosquillon. The marketability of the idea and therefore the probability for the company to get funding will be greatly enhanced by addressing both lunar and Earth extreme markets. The urgency of the demand for the solution and its desirability are high in both markets. In lunar timelines, the coming 5 to 10 years. On Earth, even faster. The challenge will be to transform LOIs into contracts successfully executed that lead to sustainable cash flow generation with actual paying customers all along the value chain in parallel with equity and debt funding. The project presentation is visually optimal. However, it underplays the hard physical and mathematical part, whereas the data is available. That aspect should be improved since it is the foundation of credibility. The obtention of patent remains a question mark. The process so far remains optimal, therefore time will tell. François Dubreuil. There are several aspects he singled out, in particular, technology interest on the Moon. 3D process specifics for use on the Moon is not clear. For example, energy supply. Soil analysis is not very relevant versus oxide conversion. Extracting iron, titanium from regolith, oxides, or ilmenite imply critical technologies. SLM 3D printing with other minerals is out of reach. Anorthosite for aluminium or densities are too few. Cobalt, chrome, nickel, tungsten, etc. Another aspect, scale up. Doubt over scaling up to reasonable mass of 3D printed parts which require further operations for effective use, not mentioning industrial scale. Supply chain issues are not addressed. Mobility and choice of deployment location is a critical factor, making soil analysis a secondary critical factor. Another aspect, business potential, backlog, and IP. Commercial potential is overestimated, thinks Francois. Contract pending terms must be clarified. What is the patent pending abstract? And the final aspect, business proposition and fundraise. Technical, financial, and commercial roadmaps are unclear, and business plan is not credible with lack of critical data like total capex estimation. Seed round proceeds remains unexplained. That's it on the part of the MBA experts, and now I give the floor to Dr. Maxim Degtyarev for the comments on the Yuzhnoye part. Please, Mr.
Дякую, пане Вінськовський. Дякую засновниці і генеральній директорці стартапа SpaceCopy пані Медісон Фіан за цей комплексний красивий проєкт, який спрямований на розроблення автоматизованої комплексної технології, яка включає всі етапи створення об'єктів місячної інфраструктури.
I would like to thank the founder and general director of SpaceCopy startup, Ms. Madison Fian, for the comprehensive and beautiful project aimed at the development of an automated integrated technology that includes all the stages of the creation of the lunar infrastructure facilities.
Незважаючи на те, що використання аддитивних технологій на місяці не є унікальною ідеєю, але створення єдиного комплексу з підготовки сировини та виготовлення конструкцій є відмінною конкурентною особливістю проєкту SpaceCopy. Також важливою перевагою проєкту є те, що технологія випробувана на імітаторі місячного ґрунту.
Despite the fact that using additive technologies on the moon is not a unique idea, the creation of a single system for the preparation of raw materials and manufacture is a distinct competitive feature of the SpaceCopy project. Another important advantage of this project is that the technology is tested on a lunar soil simulator.
Більш ефективному просуванню цього проєкту та залученню інвесторів сприятиме розкриття деяких його технічних показників, до яких можна віднести. Перше – це способи видобутку та доставки сировини та необхідна для цього інфраструктура.
More effective promotion of this project and attraction of investments will be facilitated by disclosure of the project's performance characteristics, which include the first one, raw materials extraction and delivery methods and associated infrastructure.
Далі збагачення та очищення сировини, задача, яка може виявитися досить складною та дорогою, що може впливати на економічну ефективність проєкту в цілому.
Then raw materials enrichment and purification, which may be difficult and expensive, which will affect the cost effectiveness of the technology as a whole.
Необхідно також розкрити параметри джерел енергії, особливості використання реголіту як сировини для адитивних технологій. Необхідно більш детально проробити питання постобробки точних деталей, запасних частин для всюдохідів, наприклад, космічних скафандрів тощо. Та також доцільно визначити розміри та маси будівельних блоків та проекти споруд з них, та технології відповідного будівництва.
It is also useful to indicate power supply parameters, then special aspects of using regolith as a raw material for additive technologies. Then it would be advisable to provide information about post-processing of precision parts, such as spare parts for all-terrain vehicles, spacesuits, and so on. Then it would also make sense to indicate some dimensions and mass of building blocks, then projects of buildings made of these blocks, and give some information about construction technology.
Також необхідно продемонструвати стійкість цієї технології на місяці за умов значних перепадів температур, зниженої гравітації, глибокого вакууму та інше. Також доцільно проаналізувати екологічну складову проєкту.
It is vital to demonstrate the stability of this technology in lunar environment. Here we're talking about significant temperature changes, reduced gravity, and deep vacuum. And it is also important to analyze the environmental friendliness of the project.
Також буде потрібен бізнес-план, який буде містити загальний обсяг необхідних одноразових витрат, їхній розподіл за роками виконання певних робіт, а також розміри можливого доходу та прибутку.
A business plan should also be in place, which should include a total amount of required non-recurring costs with the breakdown according to the activities to be performed in the project, as well as possible income and profit and an estimate of how this profit will compensate for non-recurring costs.
Незважаючи на ранній етап розвитку проєкту та необхідність вирішення різних технічних питань у ході його реалізації, концепція проєкту заслуговує та активність його авторів безумовно викликають захоплення та заслуговують на увагу.
Despite the early stages of the project and various technological issues to be resolved during its implementation, the concept of the project and the proactivity of its authors definitely deserve attention and inspire us.
Представлений проєкт повністю відповідає цілям конкурсу і заслуговує на найвищої оцінки. Хочу від нашого колективу та від себе особисто побажати пані Фіан успіху у реалізації її проєктів. Дуже дякую.
The presented project fully meets the goals of the competition and deserves highest rating. I would like, from myself personally and from my team, to wish Ms. Fian every success in her endeavors. Thank you very much.
Dr. Degtyaryov, with that, we move to the second project, which is presented by Iron and Steel Institute named after Nekrasov of the National Academy of Sciences of Ukraine, And the project title, I remind you, is a development of the concept of the in situ thermal dissociation of regolith oxide compounds under the influence of an electromagnetic field to produce oxygen gas in relation to lunar conditions. The project is to be presented by Mrs. Tetiana Golub. Tetiana, please.
Hello to everybody. Can you see my presentation? It's okay. Our project is about development of the gaseous oxygen by reducing the oxygen by reducing the regolith and oxides. All our team are from Iron and Steel Institute. It's Ukrainian leading research center working in the field of ferrous metallurgy. So all of us are common to metal. What do we know right now? For a long stay of people on the moon, it is necessary to create an effective technology for producing oxygen using lunar mineralogical base. What do we have? The initial conditions. Initial conditions is very low gravity, 6 times lower than on the Earth. Large temperature difference on the lunar surface, solar wind and radiation, and the vacuum. We know that moon covered with a thick layer of regolith. It's a fragmentary and loose rock material. The average chemical composition of lunar soil is shown on this slide. We know that soils in marine areas have in general high iron content, so we choose a marine area for our research. Preliminary calculation based on the known composition of the regolith allows us to determine the content of metallic iron at about 6.5%. And the formula of iron oxide will be FeO, corresponds to the mineral viscite, which has magnetic properties like iron particles. Our team proposed the technology of obtaining gaseous oxygen by means of thermal decomposition of regolith and metallic oxides under the influence of an electromagnetic field. Positive byproduct will be a metallic material. Thermodynamic calculations was done for the ferrum titanium system. Right now you can see the process highlights of our proposed processes. The complex effect of the pressure and electromagnetic field on oxides allows us to significantly reduce the temperature of oxide dissociation. This principle is the basis of smelting in a suspended state under the influence of electromagnetic field in vacuum. Since we know that the vacuum on the moon was provided by the nature itself, this approach is promising from our point of view. Melting in a suspended state is carried out by heating and holding the sample in a potential well, so-called potential well. For this purpose, the inductor, along with the main lower tones and a return upper tone, was done. Due to the difference of the direction of current flow, a zone of low tension is formed inside this coil. It's a so-called magnetic well. The lower tone serve to support and heat a sample, and upper tone to hold and press the sample into the field of the lower one. The molten sample is discharged into the wedge-shaped sample, so-called mold, this ensures high quenching rate and fixation of chemical composition. According to the GT diagram of the formation of oxide compounds obtaining for the lunar surface conditions, it means the lower pressure, much more lower pressure, approximately vacuum. It was obtained that it was determined that the reverse dissociation of oxide compounds with the formation of pure metals and oxygen is possible at Gibbs energy value above 0. So we know that for FeO, for example, the temperature will be approximately 900 degrees, and for the titanium, for example, it will be 1,600 degrees. It means that aldehyde will be decomposed at these temperatures too. So they are lower at the left side of the titanium. The practice of operating induction heating furnaces at modern metallurgical plants show us the effective possibility of their use at temperatures up to 2000 degrees. So the implementation of our process could be in their practice. The implementation of the planet technology requires minimal resource of costs. This eliminates the need of special linen materials because we do it in levitation state, in the suspended state. The only device required to obtain oxygen and metals will be the induction furnace. In case of oxygen, it will be collected at the top of the inductor by a special unit, and the metal will be held by the electromagnetic field. So the only expendable resource will be the electrical energy. We have done the test, the verification of our process using the argentum oxide because it has a low melting temperature, and you can see that we have got metal drops, so it works. Our process is possible, really working right now. So the main advantages of our proposed technology are that is minimal wear of equipment in the process obtaining oxygen, no need for consumable electrodes or fluxes or so on that are in other processes producing of oxygen in lunar conditions, and use of available structure materials and absence of thermal insulations, and the material decomposes in the state of levitation, which eliminates contact with the equipment. As we think potential consumers of our project could be companies dealing with the issue of long-term stay of people outside the Earth's atmosphere or various space objects. Thank you so much for your attention.
Thank you very much, Tetiana. And now let me present the comments by the MBA experts. I start with Akira Tsuchida. Iron and Steel Institute, named after Nekrasov of the National Academy of Sciences of Ukraine, proposed a simple method to produce oxygen and material resources from regolith. The proposed project has a number of advantages compared to existing ones. Minimal wear and tear on equipment in the process of producing oxygen, which reduces the need to supply additional components and spare parts for repairs from Earth. No need for consumable electrodes and fluxes, which are used in classical processes of electrolytic oxygen separation from regolith components. The use of available construction materials and the absence of thermal insulation, since the material decomposes in a state of levitation, which eliminates contact with equipment. As an expert for Moon surface and Artemis Gateway development, I recognize this technology helps early phase Moon development easier once developed. This proposal has a reference to their patent, and TRL is defined as 5. It is reasonable. And the R&D process and duration are reasonable. It's a practical approach. Bernd Hofer. The need for extracting oxygen on the Moon is evident. The approach seems to copy-paste an engineering approach used on Earth. The idea of using the effect of thermal and electromagnetic fields on oxides on the Moon is compelling. However, the details of how it might work and how to be implemented in the Moon environment is not discussed. It is copy-paste approach from Earth to the Moon. According to the authors, the TRL is 5, which seems to be questionable. This approach is very interesting to conduct a proof of concept in an analog habitat, which can truly simulate the regoliths on Earth. Christophe Bonal. The idea is original, excellent, and very promising in the scope of the development of lunar activities. The problem which is addressed, oxygen production, is fundamental for any future activities. The idea of having metallic byproducts is excellent. The proposed technology is original, well documented. It lacks available references, as the only one mentioned is in Ukrainian, with no translation. The functioning point is not described. What is the required power? Which efficiency? What is the production rate? It is difficult to imagine the process at industrial scale. The patent is very short and lacks details. It looks a bit like thermite, aluminothermy, and deals with materials, magnesium oxide, calcium, etc., which may not exist in the regolith, and in brackets, to be confirmed. The corresponding article in Ukrainian is hard to read, but deals with desulfurization of iron carbon melts, applicability to the moon, question mark. There are not much details on the effective tests performed so far and their results. However, it is a classical purification process already used in space stations. A TRL equals 5 is mentioned, but lacks evidence. The team appears to be highly qualified. Christophe Bosquillon, the production through electrolysis and pyrolysis of oxygen out of regoliths is costly in terms of energy and consumables, electrodes, hardware. Should that electromagnetic solution demonstrate its techno-economic scalability from prototype to lunar in situ oxygen production, it should be highly marketable and get funding. The fact that Ukraine signed the Artemis Accords in November 2020 should also be made useful to this project. A bit more co-op physical and mathematical background information could have been displayed in the accompanying material. So what is provided is sufficient to understand this novel process. The project is still in early stage. More information should be released in the coming years. Dnipro, the city of residence of the institute, is a strategic location to be defended by all means from the invaders. François Dubreuil, robust concept and high degree of feasibility. Lacks of calculations, mainly necessary input power. Lack of description, even brief, of the gas management as an output product. And now I pass the floor to Dr. Maxim Degtyarev for the comments from the Yuzhny experts. Please, Mr. Degtyarev.
Дякую, пане Вінськовський. Дуже дякую українській команді з Інституту чорної металургії за проект, присвячений видобутку з реголіту, мабуть, головного ресурсу на місяці – кисню, і як побічні продукти металевих матеріалів. На сьогоднішній день відомо про багато розробок щодо методів та установок для вилучення кисню з реголіту, однак всі вони мають певні недостатки, і пошук нових засобів є дуже важливим для успішного освоєння місяця.
I would like to thank the Ukrainian team from the Iron and Steel Institute for the project dedicated to the extraction of oxygen from regolith, the core resource on the moon, and metals, the extraction byproducts. To date, many methods and installations have been developed for extracting oxygen from regolith, but all of them have a number of significant shortcomings, and the search for new methods is very important for the successful exploration of the moon.
В проєкті вперше запропоноване одержання газоподібного кисню термічною дисоціацією оксидів під впливом електромагнітного поля. І головною перевагою цього методу є використання для термічної деструкції реголіту у зваженому стані природних умов на місяці, а саме низької сили тяжіння та космічного вакууму.
The project proposes for the first time the production of gaseous oxygen by thermal dissociation of oxides under the influence of an electromagnetic field. The main advantage of this method is the use of natural conditions on the moon, such as low gravity and space vacuum, for thermal destruction of regolith in a suspended state.
Безумовно, розробка проекту знаходиться на початковій стадії, він носить характер концепції. В ньому представлено основну ідею та теоретичне обґрунтування процесу термічного розкладу оксидів в електромагнітному полі з утворенням газоподібного кисню. Але наведені дані переконливо демонструють переваги цього методу. Комплексний вплив термічних та електромагнітних полів на оксиди дозволяє значно знизити температуру їхньої дисоціації і відповідна енергоємність методу.
Certainly, the development of the project is at an early stage. It is more of a concept since it presents the basic idea and theoretical explanation of the process of thermal decomposition of oxides in an electromagnetic field with the formation of gaseous oxygen. But the presented data convincingly demonstrate the advantages of this method, such as the integrated effect of thermal and electromagnetic fields on oxides allows significantly reducing their dissociation temperature and accordingly the power consumption of this method.
Запропонована технологія потребує мінімальної кількості необхідного обладнання та допоміжних матеріалів. Відпадає необхідність теплоізоляції, оскільки матеріал розпадається у стані левітації, що усуває його контакт з обладнанням та його відповідно знос.
The proposed technology requires a minimum amount of equipment and auxiliary materials. There is no need for thermal insulation as the material disintegrates in a state of levitation, which eliminates contact with the equipment and prevents the equipment wear.
Багато чого ще має бути зроблено. Насамперед необхідно підтвердити правильність концепції експериментально, окреслити весь технологічний ланцюжок від видобутку сировини до збирання та зберігання отриманих продуктів, розробити кількісні показники цієї технології.
Much remains to be done. First of all, it is necessary to validate the concept by experiment, outline the entire technological chain from the extraction of raw materials to the collection and storage of the end products, and develop quantitative indicators of this technology.
Доцільно також показати в ув'язці з обсягом кисню необхідні для роботи місячної бази проектні характеристики необхідного також для реалізації технологій устаткування, масу, розміри, виробничу потужність, час виробничого циклу, кількість необхідних для роботи енергетичних ресурсів, персоналу, додаткового устаткування, можливість автоматизованого безлюдного виробництва та таке інше.
In connection with the amount of oxygen necessary to sustain the lunar base operations, it is advisable to indicate the design characteristics of the equipment required for the technology implementation, such as mass, dimensions, production capacity, production cycle duration, the amount of required energy, resources, personnel, additional equipment, feasibility of automated unmanned production, and so on.
Також доцільно оцінити, скільки коштуватиме на місяці видобуток 1 кілограму кисню за допомогою запропонованого методу. Та для залучення інвесторів бажано розробити план-графік проєкту, пов'язавши його з прийнятими програмами перспективних замовників цієї технології.
It is also desirable to estimate how much it will cost to produce 1 kilogram of oxygen on the moon using the proposed method. And in order to attract investments, it is advisable to develop a master plan, connecting it with programs adopted by prospective customers of this technology.
Ну, оскільки основна ідея запозичена, з металургійної промисловості, технології швидкісної плавки під впливом електромагнітного поля у вакуумі, витрати на дослідницькі та проектні роботи будуть значно нижчими, ніж для інших методів, що не мають аналогів на Землі.
Since the basic idea is borrowed from the metallurgical industry, that is the technology of high-speed melting under the effect of an electromagnetic field in a vacuum, the research and design costs will be much lower than for other methods with no analogs on Earth.
Я вважаю, що цей проект відкриває нові можливості для одержання газоподібного кисню та металів на місяці завдяки, перш за все, ефективності запропонованої технології. Дуже дякую авторам за цікавий проект. Дякую.
I believe that thanks to the efficiency of the proposed technology, this project opens up new possibilities for obtaining gaseous oxygen and metals on the moon. I would like to thank the authors for a very interesting project. Thank you.
Thank you very much, Dr. Degtyarev. We move to the third winner of our competition, which is Dnipro State Agrarian and Economic University, with the project Development of Materials for Machines that will extract water on the moon. And I give the floor to Alexey Derkach to present this project. Alexey, please.
Thank you very much. Can you see my screen? Yes. Dear Chairman, dear ladies and gentlemen, let me thank you for the opportunity to present our lunar water extraction concept that our small team has proposed. We continue to work even under constant terrorist attack by Russian terrorist force. And only about 50 years passed between two major events in human history. The first human flight and the landing on the moon. After several American landings on the moon, its colonization came to a halt. Among the many challenges that need to be addressed for the colonization of the moon to begin in the issue of water. The colonization of the moon will only become possible after the establishment of stable water extraction there. Today, there are many ideas on how to obtain water on the moon. We already know from open source that there is plenty of water in the form of ice on the moon. Even this map, which very roughly shows the moon's water reserves, indicates that there is enough water to support human life. Many methods of the water extraction are already known. For example, the method of using solar energy and condensation, the method of separation ice from regolith using vibration sieves, and so on. The extractions of water vapor from lunar regolith by thermal methods requires high thermal power. Any heating below approximately 1000 watt per meter square produces an insignificant amount of vapor. The efficiency of such a process is still low and requires further research. Therefore, methods of separating water ice from the regolith mass without changing the phase of the water ice, mechanical separation of the mixture are of interest. This minimizes sublimation losses. In our view, the durability of moving parts of mechanical joints will become a problem in future. In our view, the durability of the moving parts in mechanical joints will be a future because such mechanism must be free from lubricants and resistant to the abrasive particles that fill the regolith. To extract water on the moon, it is necessary to use rovers with running system and working components that require maintenance. Such systems can be developed using a new polymer composite materials. They must operate at temperatures above 160 degrees Celsius and do not require lubrication. For example, we can develop carbon reinforced and other natural fibers that can function in temperatures ranging from -80 to 160 degrees Celsius. These materials will also be used in the rotation elements of regolith crushers that contains water ice. However, the performance of our materials in lunar condition still requires further research. For example, we have developed carbon plastic based on a polytetrafluoroethylene, which have a low coefficient of friction, and we have enhanced the mechanical properties by reinforcing them with carbon fibers. Similarly, we reinforce carbon plastic based on polyamide 6 and phenylone, its aromatic polyamide. We would like to study the performance of these materials in vacuum conditions and under extreme high, for example, 180 degrees Celsius, and low, minus 165 degrees Celsius temperatures. These materials could potentially be used in the moving system of the machines on the moon. We have equipment for creating and researching the properties of carbon plastics, organoplastics, and basalt plastics. These materials can be used efficiently in vacuum, high and low temperatures. This equipment has already been built during the war. There are no similar devices in Ukraine that could produce carbon plastic. We can conduct research on the effect of abrasive on carbon fiber wear, but only under atmospheric condition on earth. In our opinion, the use of self-lubrication reinforced plastic at low and high temperatures and zero of pressure is a solution to the transport problem in the technology of water extraction of the moon. What else does our team need for the final investigation? First, modeling condition of the moon. Second, to determine the abrasive effect on the developed materials, we need regolith. Next, determining the resource of the manufactured parts and then the rover. Next, cooperation with scientific institution of NASA to adapt the developed materials to specific operation conditions. Now we are open to cooperations. We are very interested in cooperations and are ready to participate in the research of water extraction on the moon, because this may become one of the steps of humanity in the future towards becoming an interplanetary species and possible survival. Thank you for attention.
Thank you very much, Alexey Derkach. And now let me present you the comments by the MBA experts to this project. Akira Tsuchida, young professionals of Dnipro State Agrarian and Economic University proposed a new polymer composite materials which work between -80 degrees Celsius and 180 degrees Celsius. Their proposal is to develop new polymer composite materials for extracting water. However, they do not need any lubrication. Therefore, they can be utilized in many other applications. Bernd Hofer, the need for extracting water on the moon is evident. The approach seems to copy-paste an engineering approach used on Earth. The idea of maintenance and lubrication-free machinery on the moon is compelling. However, the details of how it might work and how to be implemented in the moon environment is not discussed. According to the authors, the TRL is 5, which seems to be questionable. This approach is very interesting to conduct a proof of concept in analog habitat, which can truly simulate the regoliths on Earth. Christophe Bonal, the idea is original, excellent, and fundamental for future activities on the lunar surface. The principle of replacing classical thermal decomposition with friction from polymer composite with no phase change is promising and allows to remain at allowable temperatures. However, the description is very short and strongly lacks any technical background. We checked our project with mathematical calculations. It's a citation. The collection of water coming from the tribo axis of the rover is not described. One single reference in Ukrainian, but 356 pages which do not appear relevant, in brackets, acoustic waves, question mark, with no table of contents. I found the article on the page 78, but there is no technical detail. It quotes a NASA study, but gives no detail on the Ukrainian one. The claim of TRL equals 5 appears a bit high and non-justified. No additional information, but globally a good proposal. Christophe Bosquillon, extraction of water from lunar regoliths is challenging if approached with a terrestrial mindset. To develop lunar engineering solutions with novel materials for components of extraction hardware is rather astute. Should that solution demonstrate its techno-economic scalability from prototype to lunar in situ water extraction, it should be marketable and get funding. A bit more core physical and mathematical background information could have been displayed in the accompanying material. A reference in Ukrainian language has been provided and requires translation. The project is still in early stage. More information should be released in the coming years. Patents availability might be a challenge, and it's not clear to which extent the contemplated collaboration with NASA would work. The fact that Ukraine signed the Artemis Accords in November 2020 should be made useful to the project. And then Christophe asks, any potential with ESA? Finally, Francois Dubrul. Intriguing concept, outlining a good understanding of the moon challenges for water extraction. Tribology solution description remains vague and would deserve more clarifications. Questions regarding temperature compatibility with greater use of this innovation. Now I pass the floor to Dr. Maxim Degtyarev for the comments from the Yuzhny Design Office site. Please,
Дякую.
Dr. Degtyarev.
Дякую, пане Мінсковський. Ну, перш за все, хочу подякувати команді Дніпропетровського державного аграрно-економічного університету за цей проєкт, спрямований на розробку самозмащувальних матеріалів для тертьових деталей машин для використання в складі машин для вилучення води на місяці.
First of all, I would like to thank the team of Dnipro State Agrarian and Economic University for the project aimed at developing self-lubricating materials for friction parts of the machines that will be extracting water on the moon.
Проблема вибору та розроблення нових матеріалів – це одна з основних проблем, яку доводиться вирішувати творцям місячних роверів різного призначення, і це робить цей проєкт актуальним та перспективним.
The problem of choosing and developing new materials is one of the main problems that the creators of various lunar rovers have to solve, and this makes this project relevant and promising.
Вузли тертя повинні працювати тривалий час без технічного обслуговування та ремонту у складних умовах місяцю, таких як значні перепади температур, вакуум, знижена гравітація, контакт з частичками місячного ґрунту, реголіту, який є дуже абразивним і через свою неправильну форму.
Friction assemblies must work for a long time without maintenance and repair in the harsh lunar environment, while exposed to significant temperature differences, vacuum, reduced gravity, being in contact with regolith particles, which are very abrasive due to their irregular shape.
Новий композиційний матеріал має фторопластову матрицю та армуючі елементи з вуглецевого волокна. Завдяки своїй текстурі він має він має низький коефіцієнт тертя, антиадгезійні властивості та високу зносостійкість. Авторами показано, що зносостійкість за рахунок ведення армуючих рублених вуглецевих волокон збільшується до 350%, що забезпечує відповідне збільшення ресурсу роботи механізмів.
The new composite material has a fluoroplastic matrix and carbon fiber reinforcing elements. Because of this structure, it has a low coefficient of friction, anti-adhesive properties, and high wear resistance. The authors show that thanks to the introduction of reinforcing chopped carbon fibers, the wear resistance increases by 350%, which ensures a corresponding increase in the life of the mechanisms.
Вагомою перевагою проекту є також те, що матеріал розроблено та відпрацьовано в умовах землі, та розроблено відповідну технологію та обладнання виготовлення виробів з нього.
A significant advantage of the project is that the materials has been developed and tested on Earth, and this technology and equipment to manufacture products from this material have been developed.
Для відпрацювання нового матеріалу у складі тертєвих частин механізмів роверів в умовах місяця в контакті з імітатором реголіту авторам необхідно встановити співпрацю з закордонними партнерами. І ми дуже сподіваємося, що цей конкурс посприяє цьому.
In order to test the new material in friction parts of the rover mechanisms on the moon in contact with the regolith simulator, the authors need to establish cooperation with international partners, and we hope that this competition will contribute to this.
Для здійснення цієї мети, на нашу думку, необхідно продемонструвати комплексні переваги нового матеріалу за масою, економічною ефективністю, споживанням енергії під час руху машин, збільшення ресурсу роботи вузлів тертя, порівняти їх з існуючими в космічній галузі матеріалами аналогічного призначення та провести відповідні кількісні показники.
And to achieve this goal, it is necessary to demonstrate the totality of advantages of the new material in terms of its mass, cost effectiveness, power consumption while the machines are moving, its increased service life of the friction assemblies, and compare them with existing materials applied in space industry for similar purposes. It is also advisable to provide quantitative indicators.
Також треба відмітити, що розроблений матеріал може мати більш широке використання, ніж запропоновано авторами, для створення будь-яких місячних пристроїв з механічними елементами, таких як маніпулятори, поворотні механізми енергетичних пристроїв та різне інше дослідне та промислове обладнання.
It should also be noted that the developed material can be used more widely than proposed by the authors. For example, for the creation of any lunar devices with mechanical elements, such as manipulators, rotary mechanisms of power supply devices, solar power plants, and various research and industrial equipment.
Такі технологічні проекти, на нашу думку, без сумніву наближають етап освоєння людства місяця. Тому ще раз хочу подякувати авторам за конкретні відпрацьовування в лабораторних умовах розробки і побажати їм успіху в пошуку зацікавлених партнерів і використання їхніх матеріалів під час створення механічних місячних пристроїв і механізмів. Дуже дякую.
Such technological projects undoubtedly bring the stage of human exploration of the moon closer. And once again, I would like to thank the authors for tangible and laboratory-tested projects, and I wish them every success in finding interested partners and in using their materials in the creation of lunar mechanisms. Thank you very much.
Thank you very much, Dr. Degtyaryov. To wrap up this part of our program, I would like to give a floor to Christophe Bosquillon, an expert from the MBA side, for his brief remarks on every of the three projects. Christophe, please.
All right. Thank you very much, Oleg, and great to see you all today. So, as we have seen, a lot of work remains to be done for all the projects to fix all the techno-economic shortcomings. But we'd like to conclude on a positive note. First, Space Copy, well, it's a great team that has the best of Ukrainian ingenuity and North American can-do attitude. And as we all know, enterprise is about people. So great people doing tremendous work. It's interesting that Space Copy has markets on both the moon and Earth, which is better for a business plan when the company goes to the revenue phase. Also, it's important to know that Space Copy very early on has made big efforts in global outreach, marketing, communication, PR, which is why today Space Copy has already a serious brand recognition. This is very important, and many times technical venture forget about that aspect, but early brand recognition is important. And finally, Space Copy is a responsible Earth and lunar stakeholder. Madison is an active participant in a GEX-CLAD Global Expert Group, Sustainable Lunar Activities, that is run by MVS. So it's important, not just the pure business aspect, but to act as a responsible Earth and lunar stakeholder. Regarding the Iron and Steel Institute, I note it's a first-class team, the best technology and people that Ukraine has to offer. It's an alternative technology that is a game changer, very promising, and also they have solid prospect for international cooperation. And finally, the young professional team led by Alexei, there are many applications, many use cases for this technology, and maybe there's a need to select, but it's quite promising. There are markets on both the Earth and the Moon, which is important. And even though much work remains to be done, the prospects are quite promising. And finally, and I will conclude with that, for projects, we got positive feedback from our Japan expert. As you know, Japan is a strong investor in lunar activities, both the government and the commercial sector. And to get an endorsement from Japan is quite something. So I believe this adds up on the vote of confidence for all three projects, and I very positively look forward to the future. Again, congratulations to all three teams. Thank you very much. I give the floor back to you, Oleg. Thank you again.
Thank you very much, Christoph. And now, with that, we can move to the next part of our program, and which is the most pleasant, probably, which is about awarding our winners. So it gives me a great pleasure to introduce the winners' certificates. First, let me show you the certificate where all the three winners are mentioned. You can see it on the screen. So there are three winning teams this year, and represented today by Madison Fian, Tetiana Golub, and Alexei Derkach. Our sincere congratulations to all the three teams, ladies and gentlemen. Very well done. And you have heard from our experts that in general, they are very optimistic about your proposals, about your projects. They are very much interested in what you have proposed, and they spend a lot of time, believe me, to analyze and to analyze your projects and to give you their best in terms of recommendations and their knowledge of many aspects of every project. Now, I would like to present the individual certificates to each and every team, and I will invite your brief comments after that. So we start with the Canadian team, the Space Copy. Madison, congratulations again. And if you wish to say a few words, it's a good time to do now.
Thank you. Thank you so very much to Oleg, to everybody at the United States Design Office, to everyone at the Moon Village Association, and most importantly, to all of our supporters, our followers, our team, and everybody who has been with us over the past 2 years. This is an incredible opportunity for us to showcase just a little bit of what we can do, and it is my proud honor to have the opportunity to be part of such an incredible initiative that I hope to see powering future technologies for generations to come. Thank you.
Thank you very much, Madison. Congratulations again. Now I pass the floor to Tatiana Golub to have 3 comments, very short comments on the awarding of your team, Tatiana. Team of the Iron and Steel Institute, named after Nekrasov of the National Academy of Sciences of Ukraine. Congratulations again, and please say a few words to our.
Dear colleagues, thank you very much for this award. We are very appreciative of your every comment, and we understand that we just right now on the first step of our project. It's like a small step for us, but a high step for future, and we would like to continue to work by ourselves with any other colleagues and to fulfill this project as good as possible and to reach the moon with it as soon as possible, of course. And thank you so much for your high performance, and for every comment for will be very important for us. Thank you very much.
Thank you so much, Tatiana. Congratulations again. And now we come to Alexei Derkach and his team of the Dnipro State Agrarian and Economic University. Congratulations to you, Alexei, and to all your team. Please, the floor is yours.
Thank you very much, dear colleagues. Thank you very much for the opportunity to present our small idea for you. We are happy. My team is very happy, and we will be to work and continue. Thank you very much.
Okay, great. Thank you very much again, and congratulations.
Thank you very much.
You can imagine that we applaud you, everyone in his or her place, and we are looking forward to see the developments of your projects and to hear a lot of good news from every team. And I understand that Madison is going to show up at the forthcoming International Astronautical Congress. You will have some representatives from the Moon Village Association over there. So good luck, and good luck to every team in your future endeavors. With that,
thank you very much.
Yeah.
Thank you.
With that, we can move to the last part of our program today. And this is a little bit about future. I'm very happy to tell you that we are going to continue with our competition, and very soon you will have a new announcement of the 4th edition of our initiative jointly with the Moon Village Association. So please stay tuned and follow the developments on our site and the announcements that are coming. To finish with our today's program, I would like to express our gratitude to the people, to the very many people without who this competition would not be possible. And I would like to start by a statement that the preparation of the current third edition of the PromoMoon initiative was much more difficult for us than the previous two. And the reason is that the chief organizer of the PromoMoon initiative and really the engine behind the initiative, Mrs. Yulia Lysenko, tragically died. We really miss her professionalism, friendliness, and high dedication. Yulia will forever remain in our hearts. Now I would like to express our gratitude to all the team on the Yuzhny side, and I would like to name everyone who was deeply engaged in the organization and preparation, in particular, of the last session today. And this team consists of the following people: Yulia Lysenko, as it was already said, Yaroslav Lysenko, Mikhailo Kalyapin, Sergei Poluyan, Oksana Savinska, Yegor Voit, Lada Tetirko, Dmitro Gavrilenko, Yulia Arkhipova, Sergei Zakharchenko, Tetiana Kuzenko. Thank you very much, dear colleagues, for your dedication and high skills. I would like to thank Shima Suresh. It's my right hand at the Moon Village Association, who helps me a lot in performing my duties as a Moon Market Development Coordinator. And of course, I would like to express big thanks to Glavki Antonio, who is the management support team at MVA and who is absolutely instrumental in everything we are organizing under the MVA roof. Finally, my words of gratitude go to all the participants of our meeting today: Giuseppe Reibaldi, Maxim Degtyarev, Naz Al-Sakharov, Christophe Bosquillon, and all the others contributed to our meeting today. Thank you so much, dear friends, dear colleagues, and I'm looking forward to seeing you at the new PromoMoon events and at the different events which gather us together, because we all are big fans of the Moon peaceful development and exploration. Thank you so much for being with us today again, and all the best. See you in the future. Goodbye.